You know, our sun, it's the engine of our entire solar system, but it's got secrets we're only just starting to figure out. Today, we're going to talk about a brand new simulation that, by getting something completely and totally wrong, actually helps scientists get something incredibly right about how our star really works. All right, let's get into it.
So at the very heart of all this is a question that's been bugging astronomers for a really long time. What is driving the sun's magnetic cycle? You've probably heard of it. Every 11 years or so, its magnetic poles just flip. This causes everything from sunspots to massive solar flares. Figuring this cycle out is absolutely crucial for predicting space weather, and for a while now, we've thought we had a pretty solid theory.
So to really get a handle on this, we have to talk about the fundamental rules that scientists think our star plays by. For decades, there's been one leading theory that seems to explain this 11-year rhythm pretty well.
And that theory is called the Babcock-Leighton model. The core idea here is that sunspots, which are basically these giant magnetic eruptions on the surface, are the real key to the whole thing. As these sunspots pop up, fade away, and spread out, their magnetic fields all kind of merge together to build the huge global magnetic field that dictates the entire solar cycle. But, and this is a big but, for this model to actually work, the sunspots have to behave in a very specific way.
And that brings us to a super critical point, a rule called Joy's law. For more than 100 years, we've seen it. Sunspots almost always show up in pairs, and they always have this specific tilt. The leading spot, the one out in front as the sun rotates, is always a little closer to the equator. This consistent tilt is the secret sauce that makes the Babcock-Leighton model work. It's basically considered a fundamental law of the sun.
So how do you really test a theory like that? Well, a team of scientists set out to do something amazing. Build the most sophisticated, most realistic digital twin of the sun ever created. This wasn't just about proving what they already thought they knew. This was about pushing the limits of what's possible in solar physics.
And this is what makes their new model such a massive leap forward. You see, older models were often 2D and kinematic. That's just a fancy way of saying they treated the magnetic field like a passive passenger, just getting dragged along by all the hot plasma on the sun. But this new model, it's 3D and non-kinematic. And that means it includes the powerful feedback from the magnetic field itself, something called the Lorentz force. It's a two-way street now. The plasma moves the field, sure, but the field pushes right back. This is as close as we've ever come to the real thing inside a computer.
So, the team set up their incredible new digital sun, feeling pretty confident they were on the verge of a breakthrough. But what happened next? Nobody saw it coming. Their super realistic model broke one of the most basic rules in the book.
Okay, so here's the experiment they ran. They started by dropping a brand new baby sunspot into their simulation. You can see it here, a perfect little pair of magnetic poles lined up exactly east to west with absolutely zero tilt. The idea was to just sit back and watch, hoping the simulation would naturally create the correct tilt that Joy's law predicts.
But yeah, that's not what happened. Not even close. After just a few simulated days, the model didn't just fail to make the right tilt, it generated the exact opposite. The leading spot actually drifted away from the equator. The simulation had created an anti-Joy's law tilt. This wasn't some small error. This was a fundamental failure. So, this created a massive puzzle. Why on earth would the most realistic, most physically complete model of the sun get a foundational law completely, totally backward? Well, the answer, as it turns out, was hiding deep inside the invisible forces twisting the sun's plasma.
So, the scientists had to go back to the drawing board. Their simulation basically became a cosmic crime scene. They had to play detective and investigate the physics to figure out what invisible force was hijacking their model and causing this bizarre backward tilt.
And this little diagram illustrates the culprit perfectly. It turns out it's a battle, a tug-of-war between two forces. First, you've got the magnetic tension of the sunspot itself, that Lorentz force we mentioned, which tries to pull the two magnetic poles back together. But because the sun is spinning, the Coriolis force grabs onto that flow of plasma and gives it a twist. The problem was, in their model, that twist was happening in the completely wrong direction. So clearly, something important was missing from the equation. And then, the team had their breakthrough. It all came down to a single variable they hadn't considered, just how deep the sunspot's magnetic roots were anchored into the sun's interior. That one thing, it changed absolutely everything.
And this slide just shows the solution perfectly. Look at the left. That's the original failed simulation with the shallow-rooted sunspot. You can see it produces that wrong, anti-Joy's law tilt. But on the right, when they reran the exact same simulation but with a sunspot anchored deep down inside the sun, there it is. It produced the correct, positive tilt, just like we see on the real sun.
And here's the cold, hard data to prove it. This graph is tracking the tilt angle over time. That red line, that's the shallow sunspot. You can see it just immediately nosedives into a sharp negative or wrong tilt. But the blue line, representing the deep-rooted sunspot, it generates the correct positive tilt and just stays there, nice and stable. This was the aha moment. Sunspots have to be deeply rooted.
Okay, so with this new secret finally unlocked, the team could put their digital sun back to work. They had found the missing piece of the puzzle that they needed to make their simulation finally match reality.
So they went back in and tweaked the model's programming. They essentially told it, from now on, only generate these deep-rooted sunspots that naturally follow Joy's law. With that one critical fix, the simulation was finally ready for the main event, simulating not just one little sunspot, but decades of solar activity.
And the result? Well, just look at it. It's a stunningly complex and realistic simulation of the sun's magnetic surface. It successfully recreated the famous butterfly diagram pattern of where sunspots appear and, crucially, the 11-year flip of the sun's magnetic poles. By breaking their model and then figuring out why it broke, they had built the most accurate simulation of the solar cycle ever made.
This whole journey, from a broken model to a massive breakthrough, leaves us with a really exciting thought. This isn't just a simulation anymore. It's a new kind of laboratory. So, now that we have the power to build a digital sun, what other cosmic mysteries are out there, just waiting for us to solve?